Okay, so let's begin. It's my great pleasure to introduce Howard Cohl of NIST. He's going to speak on the utility of integral representations for basic hypergeometric functions, the Askew-Wilson polynomials, and their symmetric subfamilies.
Thank you, Gaurav. It's really great to be here. I'd like to, first of all, thank the organizers. It's a great opportunity for me to speak here. It's wonderful to speak to you. Also, I'd like to mention that this is a joint work with my principal collaborator, Roberto Costa Santos, who's currently in Alcalá in Spain, which is near Madrid, but I think he's moving to southern Spain soon. All right. So first, I'd like to say something about the DLMF, which is the reason. So I'm a mathematician and I work at NIST, which is the National Institute of Standards and Technology, which is a national laboratory for the Department of Commerce, so the U.S. government right? And so we maintain this website called the DLMF, or Digital Library of Mathematical Functions, and it's really great. It's a online compendium of special functions. Here's the table of contents, for instance. I use it every day in my research. So it's been online since 2010, and it's an online compendium of important properties of special functions. It's just dlmf.nist.gov, and it's an update of Abramowitz and Stegun, which is the famous handbook of mathematical functions. It's got 36 chapters written by 29 authors, each eminent mathematicians in their own specific field. Just to name a few, Frank Olver, Dick Askey, Nico Temme, George Andrews, Ranjan Roy, Tom Kornwinder. The editorial team is currently run by, well, the mathematics editor is Adri Dalhouse, who's an expert in asymptotic analysis, who worked closely with Frank Olver. And then the other editors are Dan Lozier, Ron Boisvert, Barry Schneider, Charles Clark, Bruce Miller, Benita Saunders, Marge McLean, and myself. Frank Olver, he served as the editor-in-chief and the mathematics editor for the DLMF from its beginning until his death in 2013. So the DLMF, it's a website, and its infrastructure is developed primarily by Bruce Miller at NIST, and he uses a tool called LaTeX ML, which allows you to start from LaTeX and generate a website. So it uses MathML, which is a great way of linking computer information and mathematics information, all interlinked. So the DLMF is a collection of text and formulas and figures and tables. If you haven't visited it, it's really, you should check it out. It's got really amazing properties, tons of metadata within it. So the formulas are all interlinked, as are the definitions. So if you click on a symbol, you're taken to the definition of that symbol, and all the metadata is listed. You standardize the symbols, and you can see what the symbols are, whether they're real, complex, natural numbers. We give detailed constraints. You can look for sources for different formulas, and also we're adding to it to give like proofs of the formulas or sketches of proofs. There's a whole detailed errata. And you can also find interlinking reference data. And there's a really great search engine also, so it's really easy to find stuff. And then we maintain it on GitHub, and also the current development is there as well. So, okay, so my talk today is going to be on Q calculus. Probably many of you already know about Q calculus, but I'll just give a basic introduction. So it has limits, derivatives, integrals, series, products, notion of continuity. It's not a differential calculus, it's a difference calculus. So I give the example here of the Q derivative. And if you take the limit as Q goes to 1, then the Q derivative becomes the ordinary derivative. So Q calculus is a difference calculus, but in the limit as Q goes to 1, it becomes the differential calculus that was developed by Leibniz and Newton and so forth. Typically, we take Q less than 1 but that's not necessary. You can sometimes extend Q results outside the unit circle. And there's also this notion of a Q analog. So if you take the limit as Q goes to 1, you get something that we understand in regular calculus. But not always. There are some results in Q calculus which sort of stand on their own, such as the Rogers-Ramanujan identities. But so you can think of Q as being everywhere in the complex plane, except you'd like to remove non-roots of unity, because those don't work well. But otherwise, you can treat points on the unit circle as well. Okay, if they're roots of unity. So Q calculus, going back to Euler, was able to consider this product, infinite product, as a generating function for the number of partitions of a positive integer. And so this is sort of the first view of Q calculus, and Gauss considered the basic hypergeometric series or hypergeometric series and worked on basic hypergeometric functions, but most of his work was not published until after his death. 33 years after Gauss's paper on hypergeometric functions, Heine introduced the basic hypergeometric series. And in 1904, Frank Jackson embarked on a lifelong devotion to Q calculus and systematically studying various things such as the Q gamma function, the Q derivative, the Q integral, Q Bessel functions, and so forth. And ever since then, the theory of basic hypergeometric series has been developing. Okay, so in my talk, I'd like to just introduce some basic notations. So when we have the set n0, we just mean the natural numbers, including 0. And then we have the integers, the real numbers, and the complex numbers. We'll consider a set C star, which is the complex numbers and removing 0. And then also the C dagger set will be the removing 0, and then also only taking complex function or complex numbers with modulus less than 1. We'll also introduce some other sets. So this omega q is the set of all q to the minus k's, such that k is a natural n0, and then the omega qn is the q to the minus k's, but only from k between 0 and n minus 1. You'll see why those are important when you look at hypergeometric series and some of these Q-Pochhammer symbols. You have to remove some of these sets in order for formulas to make sense. Also, we'll use some notations that you might not be familiar with. So given a set with A elements, then if the A underscore K with square brackets, you're going to remove that A sub kth element. And then if you multiply one of these vectors or a set by B, then this is what we mean, just multiplying it by each of the elements. And the same thing with addition. If you add a scalar, then you apply it to each one of the elements of the set. We also use some other product conventions. So here, if we write plus or minus A, we don't actually mean either or. We actually mean the combination of the set A and minus A. And same thing, if we write e to the plus or minus I theta, what we mean is the set e to the I theta and e to the minus I theta. And sometimes we'll also use other conventions. So A12 means A1 times A2. And A1, 2, 3, 4, 5 is A1 times A2 times A3 times A4 times A5, and et cetera. Okay, so the Q-shifted factorial, most of you are familiar with, is this finite product. And then the infinite shifted factorial here is just that product to infinity. So you might think of as infinite products as similar to infinite series. For an infinite series, you'd like convergence if the elements go to tend to 0 as the series goes to infinity. But for infinite products, you would like the elements of the series to go to 1 as the number goes to infinity. And then you would hope that there's a convergence of an infinite product. Also, we'll introduce this theta function, which is x and q minus x, because the product of these two infinite shifted factorials. And they appear quite a bit in the integral representations that we study. And then we use other standard product notations. So if you have a list of elements, then you just multiply them together, right? For the n shifted factorials or the infinite q shifted factorials. So for basic hypergeometric series, so if one of the numerator parameters, in general, we have an infinite series. So you have a r plus 1 finite q Pochhammer symbols and s denominator Pochhammer symbols. And then you have this factor minus 1 to the k, q to the k choose 2 to the s minus r. And this is your hypergeometric function or basic hypergeometric function. So you have an r plus 1 phi s with r plus 1 element numerator parameters and s denominator parameters. And then you multiply by a z to the k. So this series is divergent for r less than s. It's convergent for absolute value of z less than 1 if r equals s. And it's an entire function if s is greater than r. If one of the numerator parameters is of the form q to the minus n, where n is in n0, then this infinite series terminates, right? So then you have a finite sum, and then there's no longer any issues of convergence depending upon r and s because it's a finite number of terms. There's no question of convergence. So by the way, this is important in the study of Q orthogonal polynomials. Typically, for basic hypergeometric orthogonal polynomials, you have a terminating hypergeometric series. Also, we use the so-called Vanderbilt and Reines notation for non-terminating basic hypergeometric series. These consider the case when you have either 0 numerator elements or 0 denominator elements. And what you do is you add a superscript to the basic hypergeometric function. So you have r plus 1 non-zero numerator parameters, and then you have s non-zero denominator parameters. But then you can also have p numerator parameters or p denominator parameters. So if you have p numerator parameters, then you say it's a minus p, right? And if you have p denominator parameters, then you have a p, right? So this p in general is an integer. And if p is equal to 0, then you just get the regular basic hypergeometric series. Now you consider the denominator parameters have to be, they should not be in omega q or 0 because then this infinite series will not be defined. Okay, so, and then here are the convergence properties using this particular notation. Another notation we're going to be using is the symmetric sum. The idem function, which is common in some of the most important references on Q series, basically looks at, it's a symmetric sum. So you would like to replace one parameter A1, then you replace it with A2, then with A3, then with A4. These symmetric sums appear so often in the work on integral representations that we use. We've decided to come up with a new notation. So this I sum. So it's basically defined just to be what this idem, and it makes it much easier to work with expressions of sort. So when you see this I, think of it as a symmetric sum, and you just interchange preceding expression with all different parameters, starting with the a sub 1, for instance. Okay, so one nice thing is that the Q integral, Jackson's Q integral, which is defined here from a to b of some function, then you can actually write the Q integral as a symmetric sum. And this is actually very important. And actually it elucidates a lot of the work that Rahman has done on hypergeometric functions. So this is a nice way of writing this, the Q integral. So, and then some other properties of the infinite Pochhammer here, which we use a lot in our derivations. So we're studying Q integrals. So these are basically ratios of infinite Q Pochhammer symbols. And there are some very famous integrals, Q integrals of this sort. They're like Mellon-Barnes integrals, right? So you can write them as Q products of Q gamma functions. And equivalently, you write them as products, because the Q gamma function basically is just an infinite Q Pochhammer symbol. So this is a famous integral, which gives you the integral of the Askey-Wilson weight So this is a very nice integral. And another nice integral is a generalization of this, which is called the Nasrallah-Rahman integral. So you now add another parameter, lambda e to the plus or minus I theta, and you add another a factor. So instead of 4 a's, you now have 5. And this is given in terms of this 8W7 very well poised basic hypergeometric series, non-terminating in general. And the Nasrallah-Rahman integral becomes the Askey-Wilson integral for lambda equal to A5. And then there's even a generalization of that, which we refer to as the Rahman integral, which you can find as exercise 6.7 in Gasper and Rahman, which now you have 6 parameters, and you add the extra condition that lambda times mu is the product of all these A elements. And then you can write this integral as a symmetric sum over lambda and mu of this nice 10W9, which is a very well poised 10W9. And also, so given that lambda is not equal to 0, if you take mu equals A6 and let it go to 0, then the Rahman integral becomes the Nasrallah-Rahman integral. So then there are some other very important integrals, like some Q beta integrals. So going back to 1986, Askey and Roy derived this really nice Q beta integral in the paper of theirs. And so you've got 2 factors with an E. So the Z is there's an integration parameter psi that you're integrating with respect to. And if you write Z is E to the I psi, then you can look at terms which have an E to the I psi in the factor, or an E to the minus I psi factor, right? So then if you integrate with respect to psi from 0 to pi or from minus pi to pi, so some circle on the complex plane, then they showed that this integral is given by this nice product. Then there's a generalization of that Gasper did in 1989. We call it Gasper's Q beta integral, and this is it basically. It's another nice product. These integrals become very important in some of the applications of this. By the way, of the integral representations, especially the hypergeometric orthogonal polynomials. So this integral extends the Askey-Roy integral when e goes to 0. This becomes that. Yes. Okay, so just a little bit of history. I started looking at integrals, Q integrals, because I've been working with Tom Kornwinder on some problems in Q hypergeometric orthogonal polynomials, and in particular related to the continuous Q Jacobi polynomials. And he had some nice results on continuous Q ultraspherical polynomials, and he wanted to see if we can generalize it for Q continuous Q Jacobi polynomials. And in order to do that, you really needed some integrals, because the Q analogs are all integrals. So I thought I'd understand, and there's integral representation of Jacobi polynomials, and I wanted to understand what are the known Q integral representations or integral representations for Q hypergeometric orthogonal polynomials. A lot of work has been done on Q integrals, but I was curious about what was known about for instance, contour integrals. And if I search in Gasper and Rahman, the famous textbook on Q calculus in Q hypergeometric series, then you can actually find some information about this. And there's a couple of exercises which give, for instance, Q integral or just integral representations of the Askey-Wilson polynomials, and it leads you down a sort of a nice rabbit hole, which goes to Gasper's 1989 paper, who looks at these integrals, and these integrals go back to Slater, and so this is sort of a contour integral representation, and he showed that these products of infinite Q-Pochhammer symbols, if you integrate them, then you basically get a finite sum of non-terminating basic hypergeometric functions. And Gasper actually sent us this nice picture of a card that he had from 1984, which wrote this down. And for a long time, we were constantly referring to this card because we were using it over and over again. So this, and if you look at Gasper and Rahman, they go back to Slater's original works in the 50s, Lucy Slater. And you write down basically this, you have this integral, and you've got so you have Z, remember Z is E to the I theta in this representation. And then you have this infinite product of A, B, C, and D. So those are vectors of terms with Z and 1 over Z. and then you have an e to the im theta factor multiplied by it. So these are like moments. And then he wrote down the infinite series representations, and you can see that they're symmetric sums as well. And yes, so then it'd be like, well, this is the general case. So then how do you write these in terms of non-terminating basic hypergeometric functions? Well, you really need to use the Vanderbilt-Reines notation to do that. But then you can, no problem. So we actually, in a recent paper, which is going to appear in the Ramanujan Journal for this ASCII special volume, this is all treated. And it's also on, this work is mostly on arXiv now. So if you define this integral function, GMT, which depends on these vectors, A, B, C, and D, and then you have a parameter sigma and of course Q, then if you look at this integral function, which is, so you have a QQ infinity divided by 2 pi and a square root of t over m all raised to the nth power, and you look at this integral from minus pi to pi of this ratio of infinite Q Pachhammer symbols multiplied by e to the im psi. So in this case, z is e to the im psi. Then there's a nice property that GMT of A, B, C, D is basically equal to G minus MT, B, A, D, C. So you swap the A's and the B's, and you swap the D's and the C's, and under certain conditions of the parameters that you need for convergence. So the first case, so we've introduced this new parameter T, which is useful for a variety of reasons. You can let T goes to 1, that's okay. And it follows directly from Gasper's proof. So now we're using the Vanderbilt-Reines notation. So this integral, which we defined here on this previous slide, is just this finite sum from k equals 1 to d, where again, d is the number of elements of the d vector, and the d vector is the terms multiplied by an e to the minus im psi in the denominator, right? So this term here. So those are the critical factors for this expression. So there's d of them, right? And they're all hypergeometric functions when you write them, in general, when you write them using this Vanderbilt-Reines notation. If c equals a, so c is the terms with an e to the im psi factor in the denominator, and a is the terms which have an e to the im psi factor in the numerator, then you get this nice expression. And if they're equal to each other, then it's just a regular basic hypergeometric function. Otherwise, you have a certain number of numerator or denominator vanishing parameters in the hypergeometric function. There's also a way of writing it where you sum over the C terms. So again, so the C terms are the number of numerator parameters or denominator parameters which have an e to the im psi multiplied by them. So you can sum on the number of these parameters. And so, in fact, Slater knew this, right? Going back to the 50s, and you can write, so there's this really nice expression that you can then compare the sum over the C parameters to the sum over the D parameters. So you have an arbitrary sum, right? So you can imagine there's many ways to write this integral, and they each give different hypergeometric representations, and then they're equal to each other. Now, sometimes the argument of the hypergeometric function may not be less than 1, and the parameters may not be coinciding such that the hypergeometric series is convergent. So you'll have to be careful about that. But in cases where they are, then these two are equal to each other. And one or the other representations are valid sometimes when the parameters are such that the series are convergent. I know that I'm leaving out a lot of details, but they're just important for bookkeeping and making sure things are well defined. Okay, so one nice example of this is consider the case A equals B equals C equals D equals 2, like the simplest case, really, in many ways. Then what you end up getting is a sum of 2 4 phi 3s. So if you sum over the D parameters, you have a sum over 2 4 phi 3s. And then if you have the sum over the C parameters, you also have a sum of 2 4 phi 3s. And you see I have this T parameter here. They're equal to each other. So actually, if you look at Murad Ismail's book on basic hypergeometric orthogonal polynomials, then he has this corollary where he noticed that these sum of 2, 4, phi 3s, where you have a theta, and then you take minus theta, also you add those together, that's invariant to the same sum of hypergeometric series under this permutation where he's written down here. So this is just basically, this formula here is just a generalization of what Murad's written down. So he didn't, in fact, so in this case, these 4 phi 3s are not even balanced. So, and he noticed that. So of course, these transformations for basic hypergeometric functions are very general. They don't rely on nice combinations of parameters, balancing conditions, and so forth. Okay, so that's quite nice, and there's an infinite number of transformations that you can get of this sort, and this is just the first. So, it's important when you have sums of hypergeometric functions, non-terminating basic hypergeometric functions. So if you look at Rachman's integral, if you remember, is this integral here on the left-hand side. It relied on this factor. So you have a symmetric sum of 6. So it relied on a certain combination. If you relax that condition, now you can write the Rachman integral for any combination of lambda and mu. Remember, it used to be that lambda mu is equal to the product of all the a's. So now we can relax that condition, and you can write without that restriction as a symmetric sum of 6 10W9s of this form. So this generalizes the Rachman integral. And as a corollary, in the special case where lambda mu is equal to the product of the a's, then you get this nice transformation that the symmetric sum of 6 10W9s is equal to the symmetric sum of the 2 10W9s. But they both have argument q. So that's interesting. And you can also generalize other formulas. So here's the Nasrallah-Rachman integral, written as a symmetric sum of 5 8W7s. And then if you just compare that to the Nasrallah-Rachman integral, you get another transformation, which is a symmetric sum of 5 8W7s is equal to an 8W7. So this is, so you get another nice transformation, which would be interesting to examine. And then also you could look at like the Askey-Wilson integral. If you look at that, then if you just look at what these integrals are, then you see that they're a symmetric sum of 4 6W5s, and these 6W5s are they have a summation. You can sum them, and you can write these as a product of theta functions, and so a symmetric sum of 4 of these terms, each which are given by these theta functions, and they give you this nice product. Yeah, so that's a nice thing. Yeah, so you see that basically this symmetric sum is given by this product. So it's kind of nice, right? Okay, so looking at these integrals, it's pretty clear to see that they give you a nice way to compute this integral of theta functions or ratios of theta functions. So for instance, if you have a b theta functions in the numerator and d theta functions in the denominator, it's really straightforward to write this integral using the formula we had before, and you end up getting this GM1 of this combination of A, B, C, and D parameters, and so therefore you can write them as hypergeometric functions using the Vanderbilt-Raines notation. So this so if D is greater than or equal to B, in general you have this finite sum of these 1 phi zeros, D minus B. And for D equals B, there's actually you can actually sum this 1 phi 0, of course, using the Q binomial theorem, and you get this really nice expression for this ratio, this integral of a ratio of theta functions. So that this 1 phi 0 D minus B is actually it's a partial theta function, which some of you have worked with, I know. Ramanujan worked with them quite a lot. So Bruce Berndt and George Andrews and Ramanujan, of course, and Krishna Aladi, among others, have studied these 1 phi 0 with a superscript p with p denominator zeros. You write it down, you can see that it's this partial theta function. If you define the partial theta function as such. So you have a sum from n equals 0 to infinity of -1 to the n, q to the n, choose 2, z to the n. Then this 150p is just the partial theta function where the z is replaced by -1 to the p minus 1 times z. And the q is just q to the p. Right. So then there's all sorts of different representations for partial theta functions, just so you know, right? The theta function is given by this bilateral infinite sum. And this is Jacobi's triple product. And there's all sorts of known representations for the partial theta function as such, as a 1 phi 0, as a 4 phi 3, as a 0 phi 1 with two numerator zeros, and then or this combination of a 3 phi 2, or the 0 phi 1, as we've written before. Okay, that's kind of nice. That's just one really simple application of this theorem of Slater's. Right. So another nice result is, which actually goes back to ASCII and Roy. Really, they looked at certain special combinations of that give you these q beta integrals, and so they lead to something very natural and nice. So this integral, so where you have two denominator parameters with an e to the im psi in them, right? And then you have an arbitrary number of c's, an arbitrary number of a's, and you have this special product in the numerator where the b's appear related to the d's, right? So you have some arbitrary parameter f multiplied by the d1, and then you have a q over f times the d2. And then you have this e to the I minus im psi factor. And then you have an arbitrary parameter sigma, by the way, which allows you to change the radius of your contour integral, so you can capture the poles of the integrand. But then you also have factor an f divided by d2 and a q over f and divided by d1. Now, the nice thing is that if you multiply all of these together, you get unity, this special combination where you have the d1s and the d2s. If you just write it out, then what you can see is this integral always gives you hypergeometric functions with argument q. So this is this previous expression which I wrote out. You get the sum of two hypergeometric functions with argument q. And here I've written it here as a symmetric sum. So you always have, when you have the integrals of these form, you have a symmetric sum of two non-terminating basic hypergeometric functions with argument q. And then there's also this J representation, which is this other way where you sum over the C parameters. So, and you need that C is greater than or equal to A over 2. And this is what it is. So the J representation doesn't always have argument Q, although there are some circumstances in which it does, which I'll talk about later. Right, so this is not very, very nice. And by the way, there's also this alternate representation where you can sum over the C's. It's very natural, and if you want to see the details, the parameters get swapped, but you get basically some things that are very similar. So the C's in many ways are akin to the D's, and for this particular combination, and you have the exact same parameters, except you have the C's here. Right. So since you have a sum of two hypergeometric functions in this case with argument Q, it's a symmetric sum of two hypergeometric functions with argument Q. Actually, going back to the definition of the Q integral, you can see that this H function, which is in general an integral, can be written as a Q integral. Right. And then we've actually written it down here. So for all of these cases, you can always write these integrals in terms of Q integrals, which it's a symmetric sum in D1 and D2. And that's the result. Basically, anytime you have an integral of this form, so of course special cases include almost all the integrals that we've described. Well, certainly the ASCII Roy integral and the Gasper integral are of this form, and you can always write them as a Q integral. Yeah. So these A and C parameters are general. So some applications of this result is that anytime, or mostly anytime, that you find in literature a symmetric sum of of two hypergeometric functions with argument q, you can write them as an integral representation, and of course also as a q integral representation. And in a lot of the works of Rahman, you find he does that. You find a sum of two hypergeometric functions with argument q, and he writes it as a q integral. Right. So that's exactly the same using this theorem as writing it as an integral itself. So here's two of course, the 2 phi 1 can be written as a symmetric sum of two 3 phi 2s with argument q. There's one case where you have a vanishing numerator parameter, and there's another case where you have a vanishing denominator parameter. And I've written them as these integrals here over this eta, where eta is, so you have of course, z is used here, so I have a new integration variable, eta, that I integrate with respect to for the variable w, right? So it's just a compact notation, this w, so I have to keep writing e to the I theta, or e to the I eta, and e to the minus I eta, etc. Another case for this particular well-poised 3 phi 2, you can write it as a sum of two hypergeometric functions with argument q, and therefore you have this integral representation for this particular 3 phi 2 as well. Another case where you can write a hypergeometric function as a symmetric sum of two hypergeometric functions with argument q is Bailey's transformation for a well-poised 8W7. And this is coming from right from the DLMF. You look at this formula, you use the formulas involved, and you can easily write this as a q integral representation. And actually, you can transform an 8W7 in two ways using the two-term transformation for non-terminating 8W7s, and you have another, that gives you another q integral representation for these 8W7. Or what you can also do is use this alternate representation for the 8W7, summing over the c parameters for this integral that you get for the 8W7. And you can see that you can actually write this 8W7 as a sum of four balanced 4 phi 3s. Right. And that's actually a really nice expression. I've actually tried to see if you could actually write two of these 4 phi 3s as an 8W7 in itself, because you know Bailey's transformation gives you two 4 phi 3s, gives you an 8W7. But because of these theta functions that appear in front, where I'm using the var theta instead of the theta, that ends up being a useful notation. But you really can't write this as a sum of two 8W7s, as far as I can tell. But this h parameter here is actually a free parameter. So you can actually set it to anything as long as the functions are defined. And you can actually set it in such a way that this first term vanishes, right? And in that case, you can actually write an 8W7 as a symmetric sum of three 4 phi 3s, right? Which is also a quite nice expression. And this doesn't seem to be related to any of the other known representations for the 8W7s that I've seen in literature thus far. So these are quite nice. Okay, so now in the last part of the talk, I don't have that much time, I understand, but I'm going to talk about hypergeometric orthogonal polynomials, because this is basically the main motivation of all this work that started. So basic hypergeometric orthogonal polynomials in the Q-ASCII scheme, they satisfy James Wilson and ASCII discovered these ASCII-Wilson polynomials, and they were able to get an orthogonality relation to them. This is from Kuklinsky and Swarto. They fill out this really nice scheme of orthogonal polynomials. Then you have the symmetric ones here. So you have the ASCII-Wilson polynomials and the continuous dual Q-Han polynomials. So the ASCII-Wilson polynomials are symmetric in A, B, C, and D. The continuous dual Q-Han polynomials are 3 parameters, and they're symmetric in A, B, and C. And then there's the Asalam-Chihara polynomials, which are symmetric in A and B. And if you continue this process, you get the continuous big Q-Hermite polynomials, and you get the continuous Q-Hermite polynomials. And then, of course, there's also Q analogs, the Wilson polynomials, and the continuous dual Han polynomials, and so forth. So, for instance, the continuous Q-Hermite orthogonal polynomials are given by this finite sum, which is a terminating basic hypergeometric series, and they're orthogonal with respect to this weight function, and they have generating functions. So these are the kind of things that we're talking about. They have recurrence relations, all sorts of things, Rodriguez types, formulas, generating functions, etc. Okay, so for the ASCII-Wilson polynomials, those are 4 phi 3s, terminating 4 phi 3s, and they're balanced, which is the combination of the numerator parameters is related to the product of the denominator parameters, And so then you get this nice representation for the Askew-Wilson polynomials here, right? And then you also here, for the continuous dual Q-Han polynomials, you let the D parameter go to 0, and here's a representation for that. Okay, so what I was interested in, because the continuous Q Jacobi polynomials, those are basically just special cases of Askew-Wilson polynomials. So the question is, are there integral representations of continuous Q Jacobi polynomials? Is basically the same question as, are there integral representations of Askew-Wilson polynomials? You can actually find integral representation for the Askew-Wilson polynomials in exercise 4.5, I think it is, in Gaspar and Rachman. And here it is. I've written down the first term, this integral from minus pi to pi, and then you have these products of infinite Pochhammer symbols, which basically come naturally from the theorems which I've written down before. If you have these basically, if you write down what these are, they're 8W7s. Actually, what you get is a sum of 2 4 phi 3s, and then you can write that as an 8W7, and then it's not difficult to see how you write that 8W7 in terms of as an Askew-Wilson polynomial. And we've also got, we were able to derive another integral representation for the Askew-Wilson polynomials, which I've written down here. And actually, a student I worked with this summer, we actually derived a bunch of other integral representations for Askew-Wilson polynomials. So that this is an open topic of research to write them all down. So, okay, so here's something interesting. So Rachman derived a generating function for the Askew-Wilson polynomials, which I've given here as a symmetric sum of two 6W5s. Probably at this point, you're starting to think in your head, I can probably write this as an integral, right? Because it's a symmetric sum of the two hypergeometric functions with argument Q. And yeah, so this is a generalization of a known generating function for Wilson polynomials. Right? So as a natural Q analog, one of these terms actually vanishes when you take Q goes to 1. So this sort of, another problem I've been looking at for a while is there's this generating function for continuous dual Q-Han polynomials. That's right, not Q, this is the Q analog, as a 3F2, where you have this arbitrary Pochhammer symbol here in the numerator, gamma, it's actually arbitrary. And I was trying to find the Q analog for this, I couldn't find it anywhere. And I was actually able to find an analog for the Q inverse representation as a 3 phi 3, but this doesn't need naturally to the regular Q continuous dual Q-Han polynomials. So I was searching, and if you take Rachman's integral and you let gamma, or one of the parameters go to 0, you get this nice generating function. It doesn't have the gamma parameter in the numerator, but if you set gamma equal to 0, you see it's a symmetric sum of two hypergeometric functions, these 4 phi 3s. So this really suggests a proof by Q integral representation. And so again, you can write the representations for the continuous dual Q-Han polynomials fairly easily by taking just the limit as one of the parameters goes to 0. And there you go. It's really easy to get the generating function by using these integral representations. So you start with the left-hand side, you substitute the integral representation for these continuous dual Q-Han polynomials, and then you have an infinite sum, which you then have to integrate because it's an integral representation, and you can do that. And when you do write everything out, you can look at the proof for more details. You end up getting the symmetric sum of two 4 phi 3s, and they exactly match up in the right limit to everything that we've described so far. So I was able to get this the Q analog of this generating function, which I've been looking for several years, and I was really happy about that. But this technique is so powerful. Once I started to work on the problem, I did it overnight. I was able to get the answer easily. It was so easy. And in fact, I was also able to derive Rachman's integral, Rachman generating function as well, almost trivially. He did it in his original paper using Q integrals, but using integrals, just using the Gaspar integral, it just pops right out using known representations for these hypergeometric functions that appear. And so I thought I'd start looking at some other hard problems which people have studied in the past. Like for instance, if you want to look at moments of the Askew-Wilson polynomials, so that's basically if you have the Askew-Wilson weight, which I've written down here, and you multiply it by some x to the n, and you want to know what those integrals are. This technique is perfect for integral representations to work with it. So remember, if you have an x to the n, right, that's x is e to the I theta and e to the minus I theta, right, divided by 2. So you raise that to an n, then you have an e to the I n theta or e to the minus I n theta terms. And using, you can go back to our mega theorem, which is here. So you have integrals of this form, and you have e to the I m psi. Then we know we can write them in terms of hypergeometric functions. And when you do that, let me go back to the result, then you get this nice representation for the symmetric moments of the Askew-Wilson polynomials. So yeah, so there are actually quite a few representations known for the moments of the Askew-Wilson polynomials, but this is no one's ever really found one that's actually the symmetry, where the symmetry of the Askew-Wilson polynomials is evident. So this is a case. So it's a symmetric sum of 4 6W5s, which are not summable in themselves, by the way. Okay. Something else I treated, so I really was like, how far can I push this method? So I said, well, what about like computing the Poisson kernel for Askew-Wilson polynomials? Askey and Rahman and Seslov have a nice paper where they treated the non-symmetric Poisson kernel for Askew-Wilson polynomials. And even before that, Rahman treated just the symmetric kernel for Poisson, for Askew-Wilson polynomials. So for those of you who are not aware, the Poisson kernel is a bilinear generating function for the polynomials that are involved, where the coefficient of the infinite series is the reciprocal of the norm of the weight, right? So, so that's what you basically have here. That's what I've written down here. And there's also a generalization of that. If you instead, so typically for a Poisson kernel, you would have this, this should be an alpha here, by the way, not an X. So if you have an A, I'm sorry, it should be a bold A. And this is a bold alpha. In general are different, but you have the extra condition that alpha times gamma is equal to A times C, and beta times delta is equal to B times D. Then they wrote down an expression for the sum of 3 terms for the non-symmetric Poisson kernel. I solved the symmetric Poisson kernel, and then after I did that, I looked at the non-symmetric kernel. Actually, I originally tried to do the non-symmetric Poisson kernel, and I had a lot of difficulties understanding, because they do everything with Q integrals, and I was trying to see the way it compared to regular integrals, and you had to take advantage of the symmetry of the polynomials, and it actually was quite a bit subtle, and I actually reversed engineered it, and I was able to figure out how to do it. And so now actually I get something I think is actually simpler than what they derived. Instead of having 3 terms, we get 2 terms, and each term I've written down here. Of course, they're quite complicated, but they involve these symmetric sums. So with x is cosine theta and y is cosine phi. Then you have a symmetric sum of e to the plus or minus I theta. And you have a symmetric sum of e to the plus or minus I phi. And you have these ratios of infinite Pachhammer symbols, and it's a 4-fold sum here, which then reduce to many known representations for Poisson kernels in the Q-ASCII scheme. And you can look at all of these, and they give you nice transformation formulas. And we've started studying those, and you can do something similar. Oh, here's the second one. You can do something similar for the continuous dual Q-Han polynomials. Of course, you could just take the limit as d goes to 0. But and actually in Askey, Rahman, and Seslov's paper, they say you can do that also, but it's actually quite tricky. You just redo the derivation. You can get a corresponding result for the continuous dual Q-Han polynomials, or these other limiting cases where the Poisson kernels are known, and you can then derive interesting transformation formulas and study the problem afresh if you're interested in looking at these kinds of results. Okay, that's basically the end of my talk. I appreciate you coming. Thanks so much.
Thank you, Howard. Any questions for the speaker? Maybe you should stop sharing.
Okay.
Hi, Howard. Nice talk.
Thanks, Atul.
I just have a comment. I mean, just curious to know whether there is a, how do you make the item symbol, the elongated I? Is there in tech?
Say that again. I didn't catch that.
The elongated I symbol for item, how do you make it?
I'll return to the definition. 1 second. So it's basic. Do you know the idem function?
No, I was just asking about the symbol. Is it there in LaTeX?
Oh, how do I make it?
Yeah.
Well, that's a secret. No, I can pass you the LaTeX code. It's not that hard. Actually, I had to iterate on it quite a bit.
Okay.
Yeah, but it took actually, and also it's kind of difficult to get the factors and then above the I to be the right size, and I'm still working on the right solution to that. But it's either too small or too big. I need something sort of in the middle. But I'll share it with you if anyone's interested.
Thanks.
There are a couple of questions on the chat. If you click on the chat, you can read it. Howard.
Oh, okay. Let's see. Okay. Do they satisfy the binomial theorem type conditions? What is that? I don't quite understand. Does what satisfy the binomial theorem conditions?
You see, if you take Pn as a orthogonal polynomial system, then Pnx plus y is sigma ncj pjx and Pn minus jy, product of them. So that is a binomial theorem with the x raised to n replaced by Pnx.
I guess that's a general question about these Q orthogonal polynomials. I actually don't know the answer off the top of my head about that.
You see, many orthogonal polynomial systems satisfy this equation, and you can also combine different orthogonal polynomial systems like Laguerre alpha with Laguerre beta to have binomial type relations. And so I just wondered if your polynomials also satisfy such conditions or not.
Well, actually, I couldn't really claim them to be mine. I mean, right? They're developed by Dick Askey, for instance, and there's people like Murad Ishmael have been studying them for years and years. Yeah, I mean, other people maybe could comment on that. I'm not in a position to comment on that.
Okay, there's another question here.
Let's see. Do you consider hypergroup structures arising from linearization of product formulae? Well, you know, we are studying linearization now in detail. So that's this is something we've just started to look at. Now that I have some of the tools that I need to study these kinds of things, then of course the linearization of the continuous Q Jacobi polynomials is actually a 10W9, right? So I think it is also connected. We haven't really had a chance to look at that in detail yet, but that's something I'm very interested in. We have looked at the transformation properties of the Askey-Wilson polynomials coming from terminating representations. That's in another preprint that I'm working on with my colleague. And that's actually related to the group S6, the symmetry group S6. And we've actually studied those in terms of 8W7s as well. And it should be similar also for these integral representations. So, and then other people have studied the group structures of the transformation properties of these polynomials and these functions. They have a really beautiful structure. In fact, for the 10W9, it's actually, there's a paper by Rains and I think it's WB5 or something. They're related to these root systems that I know Gaurav has studied also. Yeah. Let's see. Is there any other questions? Did that answer your question? I hope.
Thank you. Wonderful talk and wonderful interaction.
Oh, thank you. Oh, did I use the TXZ library? Oh, no, I didn't. Yeah, I didn't actually use the TXZ library. You didn't have to. Yeah. But if anyone's interested, I can, in fact, I can paste the, let me see if I can, I can get the since two people asked me about it, I'll give it to you right now.
So
It took me a while to get it, but this is actually the command.
So
I'll put it in the chat. I'll put it in the chat window.
Is it something standard? I mean, if we use it, we won't get rejected. Or we quote you.
Well, yeah, of course, you have to define it. There it is. That's the command. Do you see it in the chat window?
Yeah. Thanks.
It just takes one argument, basically. And the argument are the numerator factors. It took me a while to get that, though. You're welcome. Yeah. Yeah, no, I definitely wanted to avoid graphics. Right.
So, Howard, I wanted to ask, what are your methods? I mean, yeah, these are really big formulas. So, is it like, I mean, is there a secret that you can tell us in 2 minutes, or is it some complicated?
Oh, you mean how I do these complicated calculations with any confidence?
No, yeah, I mean, the first integral formula, the master formula.
Yes.
What are the methods that you used?
Well, I can tell you, well, really, the master theorem is just a consequence of a result from Gasper and Rachman. They, in their chapter on contour integrals, they've basically derived that exact same result. I just made a substitution with this t parameter. It's a really trivial substitution, and then also using also the sigma parameter also, because in general you don't want the poles to be in the unit circle, so you can change the sigma parameter to force all the poles to be interior. So you have to, so it's like if you do numerical calculations, you really have to tweak that sigma parameter a lot, because the poles are moving all around and you want to capture them. Let's see, did they, right, so, oh, and originally, so we were looking at Gasper's paper, where he derived his generalization of the Askew-Roy paper, and he has this nice result in there where he writes this one integral as a sum of two hypergeometric functions with argument q, and we had seen that, but it's for very particular values, and we contacted him and said, okay, actually, then I did it for 3. I did it for 3, and I checked it numerically, and it worked. I'm like, oh, maybe this works in an arbitrary sense. And I contacted him. He goes, oh, that's actually already in our book. And you look at this contour integral results, and it's already there. And then you just write it using the Vanderbilt-Reines notation, and you're off and running from there. Yeah, and actually the result, what got us started with this, one of the things was we looked at Murad's transformation formula for the 4 phi 3s, and it really just popped out numerically if you just look at a generalization of it in terms of these integrals, and we were off and running at that point when we saw that it could explain a lot of things that people hadn't necessarily seen. Of course, like I said, Slater had did this in the 50s. You know, Gasper and Rachman revisited all of it. Of course, the proof is actually quite complicated because you can't really use the residue theorem. Well, you can, but you have to be very careful how you use it, because the residue theorem requires there be a finite number of poles, and there's actually an infinite number of decreasing poles. So you have what you do, you create an annulus, and in the annulus, it's always a finite number of poles, and you have to do things it's very subtle in the way you actually do it to get the right result. But we just relied on his. We actually did a similar result, but it wasn't quite as good. It wasn't, it didn't capture all this, but it gives you the same answer. And in the end, we just pointed to Gasper's, Gasper and Rachman's chapter result there. If you look at the current version that's on arXiv, for instance. Did that answer your question?
Yeah. I mean, obviously, it's a big secret, but I'll look at your paper to get back to you.
But it's one of the main results in Gasper and Rachman. If you really look at it, it's just staring people in the face.
This is chapter 4, right? I mean, you don't read chapter 4 so easily.
Oh, well, because we came to it from the back, really. So yeah, we didn't start from it, but we actually went to the index and we looked up Askew-Wilson polynomials,
right,
and looked up integral representation, and then it pointed us to exercise 4.5.
Right.
And we're like, well, how does that work? And that goes to exercise 4.4, which is an integral representation of an 8W7.
Right.
And then then that's a sum of two hypergeometric functions, and then well, can you do it in general? And then you can get to it from the I didn't start from it.
Thank you very much. Any
Sure.
other questions or comments? Okay, so then let's thank the speaker. Thank you very much.
My pleasure.